This conference will now be recorded.
Hello everyone. Today we are starting a new chapter which is equilibrium. So the topics that we are going to discuss today: physical equilibria, features of physical equilibria, then equilibrium in chemical processes, demonstration of chemical equilibria, and also characteristic of chemical equilibria. So first we will see some primary idea about this chapter, that is introduction. Okay. So few processes proceed in one direction, but there are different types of processes that can proceed in both directions, and that is, these processes we are calling it reversible. So that we have already seen in the chapter thermodynamics. Fine. Two types of possibilities. One is moving in one direction, but some processes are moving in both the directions. So our focus will be on this next type, that is the second type, which are reversible in nature. So here, take this example, which is not involving any chemical change. It is basically some physical change. So in this case, we will see that the process is occurring in both the directions. Here we have taken some liquid which is present in a chamber, and the chamber is closed chamber. So the molecules of liquid, which is shown in this gray color, molecules of liquid, what they will do, they will first evaporate. That means from liquid phase, now they are going to vapor phase. But the reverse process, that is condensation process, where the molecules from the vapor phase, now they are condensing and they are now coming towards the liquid phase. So this process continuously will, it will continue, fine. But remember, amount of liquid and amount of vapor, that will not change with time. So in this way, what will happen? The molecules continuously evaporating and also they are coming back. Now because of this, there will be a constant vapor pressure. So the vapor pressure is generating because of the particles that are in vapor phase, and as the amount of vapor is constant, that is number of particles in vapor phase constant, so that means that constant vapor pressure will be present. Okay, so it gives rise to a constant vapor pressure, and that is possible because of this equilibrium, that is reversible process. So in this case, we can say that number of molecules that are leaving the liquid phase equal to number of molecules returning to liquid phase, starting from vapor. So both these, that is both the directions, both the processes will continue simultaneously. Okay. So as a result, what will happen? If we plot rate, that is both condensation rate as well as evaporation rate in the y-axis and time in the x-axis, gradually what will happen? Initially, when you have taken the liquid in the closed container, first is the process of, that is the evaporation rate. Gradually, suppose it is at this point the rate is present for evaporation, gradually it will decrease with time. So see, there is a decrease. But if we see, what about condensation? Condensation rate, first it is 0, but gradually it is increasing. Now one point will reach where it is constant. So see, after this point, more or less after this point of time, the evaporation rate, that is parallel to t axis, that is x-axis, and the condensation rate, that is also parallel to x-axis. So this fixed condensation rate, which is at this point, and this one is somewhere at this point. So both the rates, now it is fixed. Okay. So this is the observation we are getting in some physical process, but it is also possible in some chemical process. So another day-to-day example, if we consider red blood cell that is present in the body, there is some hemoglobin molecules, right, which is denoted by, in short, in simple way, Hb. Now these hemoglobin molecules, they will combine with oxygen, and this oxygen is present in lungs. So now Hb, it is combining with oxygen and it is forming oxyhemoglobin. So see, now the particles, they are looking different. They are basically oxygen bonded with hemoglobin molecules, and we write it like this, HbO2. So now we have oxyhemoglobin. So there is some chemical reaction happening between Hb and O2, and then oxyhemoglobin forms again hemoglobin. So again what will happen now, HbO2, it will again form Hb and O2. So obviously it will release the oxygen molecules. Now the purpose behind it is that these released oxygen molecules, they will now facilitate the transport and delivery of oxygen from our lungs to our muscles. So in lungs, first there is combination of Hb and O2, and then from lungs to our muscles, as there is requirement of oxygen molecules, now HbO2 will be converted to again, that is, it will split to Hb and O2 again. So in this way, in our muscles, oxygen can be delivered. So these are the two examples from which you can understand that many processes proceed in both the directions, and that is actually reversible process, or we can say equilibrium is reached. Now for us, there are three important things related to a chemical reaction that we should know. It is necessary for us to know. Now these three significant aspects are basically, first of all, feasibility of the reaction. That means, is the reaction at all will occur or not? That is actually feasibility. Then the next thing is, if the reaction is possible, that is feasible, then what will be its rate? And if once we know rate, another question may also come in our mind, and that is, what is the extent of reaction? That is, how much product I can expect from this reaction. It is not rate, it is extent. That is, if we want to know yield of the product. So these three aspects are basically related to thermodynamics, chemical equilibrium, and chemical kinetics. So when you want to know feasibility of the reaction, you have to take the help of thermodynamics. So that we have already covered in the chapter thermodynamics, where we based on different laws, we talk about whether the reaction is at all possible or not, especially first law and second law. And then if we want to know the extent of reaction, that is basically from chemical equilibrium. That is all about this chapter, right? That is what will be the yield of the product once equilibrium is reached. And if you want to know the rate of the reaction, that is how fast the product will form. It is not important in case of kinetics that what is the amount of product you are getting. That is not the important point in kinetics. In kinetics, the important point is how fast you are getting. Whatever is the amount of product, that is not constant. The constant is how fast you are getting. That is the rate of the reaction that we talk about in, that is speed of reaction. Basically, it is a speed of reaction to reach equilibrium. Because once the equilibrium is reached, then the rate of forward reaction, backward reaction, both are same. So how fast the equilibrium will reach, that we talk about in kinetics, but that is different chapter. So in this chapter, it is basically equilibrium, where we talk about extent of reaction. Okay. Now this extent of reaction in equilibrium, that may also vary. That is, suppose the yield of product. Suppose you have started from the reactant A and you are getting the product B. Okay. Now suppose here 50% yield, that is starting from A, 50% of A can be converted to product. So that is why I'm saying yield of product is 50%. Now this yield, that is extent of reaction, obviously it is dependent on some conditions, experimental conditions. So when I'm saying 50%, it is obviously under such particular experimental condition. It may be concentration of reactant or temperature, then pressure, several things are there. So extent of reaction in equilibrium, that can vary with experimental conditions. So suppose by changing temperature, you can increase or decrease the yield of the product, or there are some other several factors. Okay, so all this will be discussed in this chapter. Fine. So these are the very important point, that is this slide, whatever you are seeing, that is very important, because these three in very significant chapter, if we talk about physical chemistry, thermodynamics, chemical equilibrium, chemical kinetics, what is the basic difference and what are their roles? That is, from these three chapters, the main, what is their actual significance, what are their actual application. In very simple way, if we want to say, then you have to say represent in this way. That is, feasibility is all about thermodynamics, extent of reaction you can know in equilibrium chapter, and how fast the product will form. That is better we say how fast the equilibrium will be reached, that you can understand from chemical kinetics. Fine. So now we will start the topics one by one. First is physical equilibrium, because equilibrium can be, you can achieve it in chemical reaction also, where the chemical that is composition of the molecule itself is changed. But physical equilibrium, there is no change in chemical composition. It is just some physical change will be there. So that we will focus first. Physical equilibrium. So it is equilibrium between two different physical states, that is solid, liquid, vapor. So equilibrium between these different states, suppose between S and L, solid liquid, or between liquid vapor or solid vapor, like this. Different physical state of same substance, because we are not changing the chemical composition of substance. So if you have taken water molecule, very simple example, so you will deal with its solid form, that is ice. You will deal it with its liquid form, that is a normal water, and you will deal it with its gaseous form, that is the steam or vapor. But there is no change in the chemical composition. It is still H2O, 2 hydrogen, 1 oxygen. And also the amount of matter constituting different phases does not change with time. So in different phase, suppose solid phase, liquid phase, there is a particular amount of water in solid phase, particular amount of water in liquid phase, that will also not change. Now under physical equilibrium, there are two broad categories we can have. One is phase transformation processes. So phase transformation processes, that is there is equilibrium between solid liquid or liquid vapor or solid vapor, like this. And the second one is equilibrium involving dissolution of solid. That means suppose you have taken sugar or salt, you are dissolving it water. That is actually dissolution. That means initially the sugar is in solid form, but now you are dissolving it in water. So now it is in solution form. So that is dissolution of solid. And also another one under this two heading, which is dissolution of gaseous in liquid. You can also have some gaseous that is soluble in liquid. So solid in liquid, dissolution, gaseous in liquid, dissolution. Both we will see. But first we will focus on phase transformation processes. So under phase transformation processes, we have these three. One is physical equilibrium between solid and liquid phases. Then we will discuss between liquid and vapor, and finally between solid and vapor. Okay, so one by one, A, B, C, we will see what is actually happening. And once we are done with this, next we will start equilibrium involving dissolution of solid in liquid and gaseous in liquid. Okay. So solid liquid equilibrium. Suppose you have taken some ice cubes, and there is also liquid water, that is normal water, and you have taken it in thermoflux. Now the purpose of taking it in thermoflux is that thermoflux is such a thing where exchange of heat between its contents and the surroundings is not possible, and that we actually want. We want a closed system where energy transfer not possible and matter transfer not possible. Okay, and it is also at 273 Kelvin and 1 atmosphere pressure. So under this condition, what will happen? There will be no change in the mass of ice and water, because we have taken it in thermoflux. So here you can see the picture. So this is a thermoflux, and here ice is present and water is present, and there is equilibrium, which is clear from this equilibrium sign. Now if we enlarge a small part inside the thermoflux, here you can see these are the ice cubes, right? So these are the ice cubes. Now water, that is a formula of water, you can see that is present in ice, and water is also present in liquid. So this side we have L, that is a liquid water, and this side we have S, that is water in solid form. Okay. So this system will reach a state of physical equilibrium, which means it is dynamic equilibrium. Now dynamic equilibrium means water molecules from solid state, it can move to liquid state, or the reverse process. Both are occurring simultaneously. Though it is true that the total number of water molecules in liquid phase and total number of water molecules solid phase, that is fixed once equilibrium is reached. But this conversion process, that is liquid to solid, solid to liquid, it will continue. At a first glance, it seems as the number of water molecules in liquid phase is fixed. Suppose there are total X number of molecules in liquid phase. There are total Y number of molecules in solid phase. And this number is fixed once equilibrium is reached. So it seems at a first glance that there is no movement occurring. But actually movement is occurring. And the movement is occurring in such a way that the same number of molecules moving from S to L and same number of molecules coming from L to S. And that is why this number is fixed. It will not change. So as this number is fixed, but still the process is going on. So that is why we call it dynamic equilibrium. It is not static equilibrium. So total number of water molecules leaving from and returning to solid phase at any instant, that is equal. We can also say in terms of rate, that rate of melting of ice. Basically, rate of melting of ice means what? The number of water molecules leaving from solid and reaching the liquid state. That number, that is actually the rate. And the rate of freezing of water, that means number of molecules from liquid phase to solid phase. That is the freezing process. So these two processes at equilibrium, the rate is fixed. It is obvious that ice and water, they are at equilibrium only at temperature, particular temperature, pressure. So remember, you have to fix temperature and pressure. Otherwise, you cannot reach this type of condition. So that is why at the first point, it is clearly mentioned that it is 273 Kelvin and 1 atmosphere pressure. So you have to fix it at some value. Here we have taken 273 1 atmosphere. That is a standard. Mostly we take these conditions for pressure and temperature. You can take any other pressure, temperature, but important point is it should be constant. Whatever value it is, it should be constant. Now when it is 273 Kelvin and 1 atmosphere, if you maintain this type of temperature and pressure, now we can say for any pure substance at atmospheric pressure, that means at 1 atm pressure, the temperature at which solid and liquid phases are at equilibrium, that is called normal melting point or normal freezing point. Okay, so we know it is basically 0 degree centigrade, and 0 degree centigrade means 273 Kelvin. So when you are fixing the pressure, automatically there will be a temperature where this equilibrium will be reached, and that is called normal melting point or freezing point, and that is basically this 0 degree centigrade. Okay, now if you change the pressure from 1 atmosphere, suppose you are increasing the pressure, decreasing the pressure, obviously now this freezing point, that will also change. It will not remain fixed. Next phase equilibrium we will see, which is between liquid and vapor state. When liquid evaporates in the closed container, you have to take closed container always. In the previous case also we have taken thermoplast, now we have taken also closed container. Now the liquid molecules escape from the liquid surface into the vapor phase and building up some vapor pressure. So initially what will happen? The molecules from liquid surface, especially from surface, not from bulk, they will be converted to the they will reach the vapor phase. And as the number of molecules from liquid surface, they are moving towards the vapor phase, obviously the pressure because of this vapor, which is basically vapor pressure, that will increase. Now once it is this process just started, the next process, that is the condensation process. Now the molecules, they will come back to the liquid state from the vapor because the container is closed. They cannot escape out the container. They have to remain in the container. So there is only one possibility, they will be converted again to liquid. Now once the equilibrium is reached, the vapor the pressure exerted by the water molecules at a given temperature that remains constant. So this pressure is constant, and this is actually the equilibrium vapor pressure. Now, as it is already mentioned that at a given temperature, that means it is dependent on temperature. So once you fix the temperature, there will be a pressure exerted by water molecules, because in this case we have taken water molecules. This pressure is constant, which you are getting at equilibrium provided temperature is constant, and it is called equilibrium vapor pressure of water, or simply vapor pressure of water. Mostly we call it vapor pressure of water, and if it is any other liquid, then vapor pressure of that liquid. In this case it is vapor pressure of water. So at equilibrium, just like any other process, we have also had seen this before, that rate of one process and the reverse process, both the rates are same. So rate of evaporation is equal to rate of condensation. But you also have to remember that it is temperature dependent. So once you increase the temperature, obviously now the rate of evaporation will increase, and also vapor pressure of water, that will increase. So it is directly related to temperature. An important point, it is not possible to reach equilibrium if your system is open. So instead of taking closed container, suppose you have taken some open beaker. Now what will happen? Condensation is not possible. If the container is closed, the molecules that are already in vapor phase, they have no other way but they have to come back to the original phase, which is liquid phase. They cannot escape the container. But if it is open, now they can march to the surrounding atmosphere, right? So if you want to reach equilibrium, you have to take closed container. Open system will not work. Now just we have given the definition of normal freezing point. Here also you can give the same type of definition, but now it will be boiling point, because we are converting liquid to gaseous state. The temperature at which vapor pressure of liquid is equal to external pressure. External pressure, mostly in surrounding, we know it is in general we consider 1 atmosphere. So another way also we can say that at 1 atmosphere, the vapor pressure of liquid, it is equal to this 1 atmosphere, and this is actually the boiling point at that pressure. And mostly it is 100 degrees centigrade when it is 1 atmosphere pressure, that we consider for external pressure. That is for surrounding, under general state it is basically 1 atmosphere, right? So this is the definition of normal boiling point of a liquid. This is a basically definition of boiling point, because when we are giving the definition of boiling point, I am not saying it is normal boiling point. Suppose we are talking about only boiling point. Now that depends on what is your external pressure. It is true, in general we consider 1 atmosphere, but suppose forget about 1 atmosphere. Suppose it may be any temperature, any pressure. At high altitude it may be different, at low altitude it may be another type of pressure. So in general it may be, suppose if any pressure, general definition of boiling point will be the temperature at which the vapor pressure of this liquid, it is equal to external pressure. And this boiling process can start only when this container is no longer closed. So once it is closed, this equilibrium will be there. But once the vapor pressure, it is reaching the external pressure, under that condition, if the container can be open, now boiling process will start. Because once the boiling process is starting, now the molecules in the vapor phase, this condensation will no longer be there, because now we have opened the system. So this is boiling point. But if we talk about normal boiling point of a liquid, it is that temperature at which vapor pressure is equal to 1 atm. So now we have fixed this external pressure to 1 atm, and mostly it is 100 degrees centigrade when boiling process starts, because only at this temperature vapor pressure equals to 1 atmosphere. Okay. Now related to this, if we discuss this problem, it will be clear. So it is assertion reason type of question. In assertion, it is saying normal boiling point of water is 100 degrees centigrade. There is another term we use, which is standard boiling point. So there is a basic difference between normal boiling point and standard, though it is almost same value, but still there is some difference. So when you are calling it standard boiling point, it is 99.6 degrees centigrade. When you are calling it normal boiling point, the definition that you have just seen in the previous slide, then it is 100 degrees centigrade. So this assertion that is actually true. Now reason it is mentioned that the temperature at which vapor pressure of liquid is equal to external pressure is called boiling temperature or boiling point at that particular pressure. Now this is also true, as this we have just seen as a definition in this. See, this part is basically mentioned in the reason. So reason individually, if we say, because it is assertion reason type of problem, first of all you have to understand that individually the two statements are true or not. So in assertion is true, reason is also true. Okay, now if that is so, C and D, these two options are not possible because both are correct. But whether the second, that is the second statement, that is a statement in reason, it is a correct explanation or not the correct explanation, that we have to check. Now normal boiling point, we have seen the definition in the previous, it is at 1 atmosphere. And standard boiling point, what is the definition? Standard boiling point definition is, now the pressure is considered as 1 bar, not atm. Now atm and bar, these two are almost same unit. There is subtle difference. So what is the difference? At 1 atmosphere pressure, boiling temperature is called normal boiling point. But if the pressure is 1 bar, now the boiling point is called standard boiling. That is fine. But what is the relationship? Relationship is this. 1 atm is basically 1.01325 bar. That means 1 bar pressure. If you directly compare with 1 atm, it is slightly less. That is why when we are equal sign is there, that means it will be slightly high value you have to write for bar. So 1 bar pressure is slightly less. And as boiling point is dependent on pressure, so when there is high pressure, that means 1 atm is obviously high pressure, then the boiling point is 100. But when the pressure is 1 bar, which is slightly lesser than 1 atm, obviously the boiling point will also be slightly lesser than 100 degrees centigrade. And that you can see here, 99.6, it is slightly less than 100. So this is directly related to this explanation. That is the temperature at which vapor pressure of liquid is equal to external pressure. So when it is external pressure 1 atm, now required temperature for boiling, that is the required temperature at which vapor pressure of liquid will be equal to external pressure, that required temperature is 100 degree. But when the external pressure is 1 bar, now the required temperature for boiling point is different. Slightly different, but still different. 99.6 degrees centigrade. So therefore, standard boiling point of liquid is slightly lower than the normal boiling point. So here option B should be the correct option. Is the correct explanation, and both are individually correct statement. Okay. Now we have reached the third phase equilibria that is possible, solid to vapor. Now this is possible only in few cases because sublimation process, it is not very common. Sublimation process is directly from solid it will be converted to vapor or vice versa. Normally what happens? Solid to liquid, then liquid to vapor, or vapor to liquid, then liquid to solid. But directly solid to vapor, that process is known as sublimation process. So this is possible, that is, it is only for those examples, that is only for those solids where direct sublimation is possible. It is not applicable for all solids, it is specifically applicable for few solids, right? Provided where sublimation is possible, and very good example is iodine as a solid. So when we take solid iodine, it looks, if we look at the crystals of solid iodine, it looks almost black, but actually it is not black. It is so intensely violet, it appears as black. Okay. Now once you placed it in closed transparent vessel, it has to be transparent, otherwise you will not be able to observe the color. So if you have taken a transparent vessel which is closed, then you will see after some time the vessel gets filled up with violet vapor. That means from the solid iodine, vapors are generated, and because of this sublimation process. Okay, so this is the picture. These are the crystals of iodine, which looks almost black, but actually it is very intense violet. And then there is vapor, and this vapor, that is also violet color. So if solid iodine placed in closed vessel, violet start appearing in the vessel, and gradually the intensity of color of this vapor will increase. But remember, ultimately there will be a point where this became constant as the following equilibrium is attained. So as first you start the process, there will be no violet vapor, then gradually there will be some violet vapor, and the intensity will increase, and once equilibrium is reached, now there is no longer increase in the intensity of violet color of vapor. Fine. So this type of equilibrium, iodine solid to iodine vapor and vice versa, once it is reached, then the color intensity in the vapor phase, that will be fixed. So at equilibrium, what we can say, that rate of sublimation process of solid iodine is equal to rate of sublimation process, rate of violet, that is vapor form of iodine coming back to solid, that rate, these two rates will be constant, same, not constant, I mean the rate of sublimation from solid iodine to vapor and the reverse process rate, both these will be same once the equilibrium is reached. So A, B, C we have covered. All these three are related to different phase equilibrium. Now the second point, which is equilibrium involving dissolution of solid in liquid, number one, and then gaseous in liquid, number two. So first we will focus on solid in liquid. Now we will take some salt and we will dissolve it in water. Dissolution of solid in liquid. When we add salt to water at a particular temperature, obviously temperature should be fixed because solubility dependent on temperature. You have to keep the temperature fixed. So it dissolves to from salt solution, and gradually you are increasing the amount of salt, but a stage will reach when you no longer can add further salt, because whatever amount extra you are adding, they will precipitate and there will be solid. You can observe that in the, if the container is transparent, that is solution, it will not dissolve anymore. So it means what? That saturation state is already reached. So the resulting solution, now we can call it saturated solution. Once you start noticing the solid salt in the bottom part of the container, okay, that means now it is saturated. Now at this stage, what happens? As many molecules of salt from the surface of solid salt go into the solution state, and same number of molecules of salt that are present in the solution state, they deposited back on the surface of solid salt. So this is equilibrium. So this equilibrium is now established from this pictorial representation. So this is the crystal of salt, sodium chloride, right? Now first there will be molecules from the surface of the solid salt will go into solution, and this is the direction, right? So see all the direction towards this solvent. This is the solvent, and the molecules that are in solvent, now they are also coming back. And one time, first what will happen, see, three arrows for simplicity, only three arrows towards this direction, from solid surface towards solvent it is moving, and only one molecule is coming back. That means the rate of the going from the surface of solid salt to the solution, that rate is high. But once equilibrium is reached, now both the numbers are same. So now see, these two arrows moving from solid state to solution state, and these two arrows are opposite. Two different balls you can see here. One is for cation, Na plus, another one is for anion, Cl minus. Okay, so dynamic equilibrium is established between the solid molecules in the solid phase and the solution phase. Okay, so this is dissolution of solid in liquid. You can also have the same situation if you take sugar instead of solid. Dissolution of gas in liquid. Now instead of taking solid, you can also take gas molecules. When a gas dissolves in liquid under a given pressure, because that is dependent on pressure, so we have to keep pressure fixed. There will be equilibrium between gas molecules in the gaseous state and those gas molecules that are dissolved in the liquid. Fine. So we will take the example of sealed can of soda water bottle. So as it is sealed, the pressure of the gas, that is sealed container, soda water. Soda water means carbon dioxide present in water. So here the gas involved is carbon dioxide and the liquid is water. This is CO2, this is water. The pressure of the CO2 gas is very high above the liquid. So the mass of the gas dissolved is also high. So at a first, when the process will start, mass of the gas dissolved is high because the pressure of the gas is very high. With increase in pressure, the dissolution of gas in the liquid phase, that actually increases. Fine. So see, CO2, these are the CO2 molecules and they are under pressure. So suppose this part there is no liquid, only CO2 molecules are there above the liquid, and these are the CO2 molecules that are already in solution. Now if we open this container, what will happen? There is basically these CO2 molecules, they are actually under pressure. Normally they do not want to remain in the solution state, but somehow they are in the solution state only because we have this sealed container. Otherwise CO2 will not dissolve in water. Only if there is high pressure you can have CO2 dissolved in solution, otherwise not. So once you open this, they will immediately released. Okay, so equilibrium that we are talking about, that is possible only when it is closed, only for this system, not for the other. The second picture is given here so that you can understand that once the pressure is released, the CO2 they will be coming, they are escaping from the solution phase, and that is why we see some bubbles once we open the can. As soon as bottle is open, the pressure tends to decrease to atmospheric pressure, because the outside pressure, atmospheric pressure, obviously this is lower than the inside sealed can pressure. Inside the can there is high pressure, that is why CO2 is dissolved in water, otherwise you can't get it, right? But when it is opening, now they are decreasing to atmosphere pressure, and that is the reason now solubility will decrease, because solubility is directly related to pressure. And the dissolved gas, now they are escaping in the form of bubbles. Now these phenomena occurs because of difference in solubility of CO2 at different pressure. So suppose if CO2 and there is high pressure inside the can and outside there is low pressure. But suppose if both these pressure are at both this pressure, CO2 is having same solubility. So obviously this type of when you open the can, they are releasing in the form of bubbles. All this you will not observe. You are observing this because the solubility of CO2, when it is high pressure, it is one kind of solubility, that is high solubility. When it is low pressure, then it has low solubility. So that is why they are escaping. They don't want to remain in the solution state, right? So this phenomenon occurs because of difference in solubility of this gas at different pressure. Now here we have a law. Details of this law that is in class 12 chapter, which is solution. But we can have some idea just to understand how it is related to pressure, directly related to pressure. The amount of gas dissolved is governed by Henry's law, and this law states that mass of a gas that will be dissolved in a particular mass of a solvent, provided temperature is fixed, that is directly proportional to the pressure of the gas above the solvent. So that is that it is basically, it means this statement that phenomena occur because of difference in solubility. That means it is directly proportional to pressure. Here it is high pressure, solubility is high. Here it is low pressure, solubility is becoming low, and that is why they are going back to the atmosphere. They no longer want to remain in solution because you have decreased the pressure. So this is Henry's law. When a particular mass of gas you are trying to dissolve in a particular mass of solvent, in this case water, at any temperature, because you can't change temperature, it is also dependent on temperature. So temperature should be fixed. Then only you can understand the relation of solubility of gas in a solvent, the relation with the pressure. So it is directly proportional to the pressure of the gas that is present above the solvent. So dissolution of gas in liquid, that we have finished with the example carbon dioxide, and the liquid is water. Features of equilibrium. So physical equilibrium, what we have seen, basically we are now doing the summary, whatever we have discussed. We have seen solid liquid phase equilibria. We have also seen liquid gas, then solid and solution, gas and solution. So these two we have covered just now, and these two we have covered initially, right? So for solid liquid equilibria, there is only one temperature. Remember, solid liquid equilibria, we have taken ice and water in thermoflask, that example. There is only one temperature which we call as melting point, and at 1 atmosphere it is almost close to 1 bar. Slight difference is there, at which the two phases can coexist and there will be equilibrium. Then the next point related to liquid vapor. So we have taken closed container, there is some liquid water, and some molecules from liquid surface, they are moving towards vapor phase. That example. For liquid vapor equilibrium, the vapor pressure is constant provided temperature is fixed. Vapor pressure means the molecules that are escaping the surface of liquid and they are going to the vapor phase. These molecules, they will create some vapor pressure because the system is closed. Fine. Then the fourth point, dissolution of solid in liquid. Suppose salt you have taken in water or sugar in water. Solubility of the solid, that is solute in this case, in the liquid, solvent in this case, it is constant at a given temperature. So if you increase temperature, mostly it is observed solubility is also increased. And for dissolution of gases in liquid, the last example, soda water can, the concentration of gas in liquid is proportional to the pressure of the gas over the liquid. So these are the summaries that we have obtained from these 4 different physical equilibria examples. Now what about chemical equilibrium? Chemical equilibrium is now the chemical composition of the molecules will change. So here we have this general equation. You have started from A plus B. These two are basically reactant, and you are getting two products C and D. Now when you start the reaction, at a first initially concentration of these two, obviously it will be high compared to C and D. And not only high, they will be at a maximum point. So suppose these are the, just compare the color, this is maroon color. So these are the reactants A plus B. So they are at maximum concentration, and the concentration of products, it is 0. From the y-axis it is clear. Now gradually what will happen? The rate of forward reaction is okay, come to the rate first. So the second graph is concentration versus time. So this line, maroon line, is for A plus B, and the blue line, that is for C plus D. Now what about reaction rate versus time? Forward rate, that means the conversion of AB to C and D, that rate is maximum initially. Initially means when time you are starting here, and the rate of reverse reaction, that is minimum, it is actually 0. So backward reaction rate is 0. But as time you are moving towards this direction, as time is increased, now what will happen? That is, the reaction is now started. A and B react to produce product C and D, and thus the concentration of A and B will decrease. That is clear from this. It is decreasing. Okay. And thus concentration of that of product increases. So product concentration is increasing. Now look at the rate. In case of rate, what will happen? The rate of forward reaction gradually from this point, now it is decreasing, and the reverse rate from 0, now it is increasing. So this is expected. Next, what will happen? So just see the previous picture. We ended the two graphs here. But if you, that is up to this time point, we have seen what is happening up to this time point. But further, what will happen when equilibrium is reached, that we have to see. So after this point, if you further move right hand side, that is time you are increasing. Now what will happen? One time will reach when both the red line, they are merging to each other. That means they are becoming same. And this equal rate is somewhere here, the value, if you extend this line. Similarly, once the time is reached here, it is decreasing, it is increasing. But one point will reach where this is parallel to time axis, this is also parallel to time axis. And the equilibrium concentration of reactant, if you extend the line, it is somewhere here. Equilibrium concentration of product, it is somewhere here. So a point will be reached when the rate of forward reaction is equal to rate of backward reaction, and the state of the reaction is called chemical equilibrium. It is reached, and at this state, concentration of reactant unchanged, concentration of product unchanged. So that is why it is parallel to x-axis. I am not saying that reactant concentration, product concentration same. I am just saying that there is no further change in their amount. So reactant concentration fixed at this point, product concentration, reactant is fixed at this point. This is reactant A plus B, and product concentration, it is fixed as this point, because this line is for product, this line is for reactant. Okay. It means that at equilibrium, neither forward or backward reaction stops. So don't think that reactant concentration fixed at this point, product concentration fixed at this point, but this does not mean that forward reaction stopped, backward reaction stopped. No, they are both continuing at equal rate. It is still continuing, okay, but the rate is fixed. That is fine. So the equilibrium is reached, and it is not static equilibrium, it is dynamic equilibrium. So it seems as if everything is stopped, but actually it is going on in such a way that C plus D concentration is fixed, A plus B concentration is fixed. So you can visualize this with this picture as if you have taken some water and there is some outlet where water amount is decreasing. But in a similar way, the same amount of water is also coming. So the water amount that is decreasing and the newly added water, if both are same, obviously this total quantity, it is fixed. Just compare that the concentration of CD fixed, concentration of AB fixed. But this water is pouring here and water is also pouring here. This process is going on. It is not that the tap water we have closed. No, it is not. Water is flowing, but amount in the container, amount of water is fixed. So you can compare with this picture. It is to be noted that reversible reactions involving gaseous substances. Here this A, B, C, D, whether it is gaseous substance or not, that we have not said anything about. But suppose if they are gaseous substance, obviously you have to use closed vessel. Otherwise what will happen, there is a tendency, as it is gaseous substance, there is a tendency it will escape the vessel. And once it escapes the vessel, mass is not fixed, then you cannot have all these conditions. These conditions you can only have if mass is not escaping. And there is a chance of mass escape if it is involving some gaseous substance, not applicable for solid liquid. But for gaseous substance, if you want to achieve equilibrium, you have to take closed vessel. Okay. Now this is for general example we have seen, but if we actually want to demonstrate chemical equilibrium with actual example, now we have taken this reaction where we start from hydrogen and iodine and we are heating it in a closed vessel because they are gaseous, and you are getting the product 2 hydrogen iodide molecule, all are in gaseous state. At a first glance, initially when the reaction is just starting, the color of this mixture will be deep violet because we know solid iodine is violet color, and initially the concentration of reactants are high, so there will be deep color, violet color. You can see it if it is transparent container, and it is because of this starting material iodine. Now the reaction starts at this temperature 717 Kelvin. The reaction now starting. Gradually, as iodine is consumed, that is, it is reacting with H2, so its amount will be consumed. Gradually, the deep violet color of the mixture, it is becoming faint and faint. So it indicates that iodine is consumed, it is reacting with H2, and that is the proof the color intensity is decreasing. After some time, what will happen? Now you will see the intensity of violet color, it is now constant. It is not that all the violet color removed, it is not that. There will be some color still present because still there is some iodine. It is not that all the iodine converted to HI. No, some amount converted, some amount is fixed. But once equilibrium is reached, now the amount of iodine is fixed in the gaseous form because the solid form is not reacting. It is converted to because of sublimation, it is converted to gaseous, and that is reacting with H2. So now it means, it indicates that the reaction is stopped, although both of these starting materials are present, but equilibrium is reached. So here we have taken reaction rate in y-axis and time in the x-axis. Suppose here just focus on this black line where H2 and I2 we have started, we are getting HI. And even if you start the reverse process, suppose you have not started from H2 and I2, you have started the process by taking some hydrogen iodide. In that case also, the reverse reaction, that is H2 and I2, it will form. Now this formation of H2 and I2 starting from HI, it will increase, and once this point is reached, now see this reaction rate, it is fixed. So this is the forward reaction rate, this is the backward reaction rate. But once equilibrium is reached, both the rate are basically same. If you extend the line, you will cut it somewhere here. So this is the equilibrium. That is a combination of these two reactions. If you write, you have to use this double-headed arrow, so it will be represented in this way. So same type of picture we have also seen in the previous graph. Remember, where forward rate, reverse rate, both are same, and you are getting some equal rate. So even if you start from the opposite, suppose HI is the starting material. If you start from this type of condition, then also you will get H2 and I2 as product. So here the purpose is amount of H2, I2 and HI, all these three compounds, they are actually fixed. The equilibrium concentration of all these three are fixed. So whether you start from HI or you start from H2 and I2 mixture, ultimately you will reach this point where both this rate, that is the forward and backward, both are same. Now here we have these two reactions written individually, forward, reverse. Chemical equilibrium you can achieve, it doesn't matter from what point you have started. So it can be attained whether the reaction begins with all reactants and no products. So suppose you have started like this, all reactant, this is reactant, and no products, or all products and no reactants. That is, you have started from product and no reactant. Or this is two extreme condition you can start it. Or suppose you are starting by taking the mixture of all these three in a certain amount. That also you can do. But whatever you do, all these three possibilities, you will always, you can attain equilibrium. So it doesn't matter from which point, that is what mixture you have started with, because ultimately the amount of these three will be fixed. That is, equilibrium concentration will be fixed. So here, concentration versus time. Gradually, if you consider this reaction, gradually the amount of HI is increased, the green line, and the amount of H2 and I2, this is the starting point, that is decreasing. Similarly, if you start with only product, so you are starting with product and product concentration at equilibrium, this is actually the point where equilibrium is already reached. So see, it is somewhere here, the equilibrium, concentration of HI. Same thing, this is the equilibrium zone after this point. Here also, if you extend the line, it will cut at the same value. So this is the equilibrium concentration of HI. Here also, this is the equilibrium concentration of HI. But you have started with HI, so the concentration of HI is somewhere here. But gradually, it will reach the equilibrium concentration. Similarly, if you consider the first reaction, where after this line, or this, whatever, the concentration of H2 and I2, it is cutting somewhere here. This is the point. Here also, you have not started from I2, H2 and I2. You have started from HI. But gradually, the amount of H2 and I2, it will decrease. And that is, with time, it will be fixed. It will increase. Because initially, the amount of H2 and I2 is 0. You have started only from HI. Amount of H2, I2, initial time, 0. But gradually, it will increase. But ultimately it will fix at this point. If you extend the line, it will cut here, which is same as this value. That means whatever point you start, whether you start with all HI or all H2 I2, it doesn't matter. After all, you will reach these two values of, this is the product concentration, this is the reactant concentration. So this is graph A and this is graph B. If you take, if you merge these two graphs, the nature of the graph will be something like this. So C is the graph which is the combination of these two. So see, in the left hand side, this is the equilibrium position compared to, that is, suppose this is the time where equilibrium is reached. So suppose that is the point here. So this part you can find similarity with graph A, right? See, there is some similarity in the nature. But if you focus on this part, you can find some similarity as if the graph B, just if you flip it, that is, if concentration axis, if you take this side, just flip it, then the nature of the curve, it will be just like B. So this part is basically B and the left hand side is basically A. So it is the combination, that is, both the graphs are merged. So this is the equilibrium point reached, and the concentration of HI, it is now parallel to this axis. That means it is fixed at some value, and the concentration of reactant also, it is fixed at some value. Okay, so we will end here. Thank you for listening.